Welcome you all in my next class of my channel Ganit Setu. And today I am going to connect you for a chapter relation and function. Basically it's unit 1 of class 12 CBSE, which has two parts, relation and function as well as inverse trigonometric function, both together weightage 8 marks. And you can see the syllabus in the reduced and modified syllabus. It's about relation. When you talk about relation, it's a domain, range, and three types of relations are there: reflexive, symmetric, and transitive. While the functions, there are two types of the functions: one and on2. When you come to inverse trigonometric functions, their range, domain, and their graphs is simple. So today we'll discuss about relation and function, which is very interesting topic of unit 1. When you say relation, we all are related to one another through one another relation. Maybe X is a student of Y, so Y will be a teacher of X. If X is a brother of Y, it depends upon Y, whether Y is a brother of X or sister of X. So in all our daily life, we are always connected and have some kind of relations. So whenever you say that X is related to Y, we write it as X or Y. X is related to Y, or as simply we can write as ordered pair X comma Y belongs to relation. So basically, what is a relation? Relation, whenever we talk about relation, there are two families, A and B. These are two non-empty subsets of the set of real number. If you are talking about real number, or it can be in two families, family of triangles, family of lines, all these things. So these are two families, and if you are connecting the members of A to B, so we say that X belongs to A, and X will take as any element of A, and it will Y any element of B. So when you are defining a relation, there will be a collection of all possible ordered pairs X comma Y, where X belongs to A and Y belongs to B. And before you study relation, I think you might have studied Cartesian product in class 11. Cartesian product, cross product of two sets. When you study set theory, what you study? A cross B. What is A cross B? It is also collection of all possible ordered pair X and Y, where X belongs to A, Y belongs to B. That is Cartesian product. But here, what is the difference? Relation is a collection of all those ordered pairs where X belongs to A, Y belongs to B, as at the same time X must be related to Y through well-defined relation. Only those ordered pair will include in relation. So what you observe and understand, that relation is a subset of A cross B. Clear? A cross B is a collection of all possible ordered pairs of the elements of A and B. But relation is a collection of only those ordered pairs of X and Y, where X is a member of A and Y is a member of B only when X and Y are related through well-defined relation R. Now it depends upon which families we are talking about. So I will illustrate through some examples. So we are taking here two sets, right? Set A and set B. Suppose set A has 3 entries, 1, 2, 3, and set B has entries 3, 4, 5. Now when we say A cross B, so for every element of A, there are 3 elements of B. That means the possible ordered pairs will be 1, 3, 1, 4, 1, 5. Similarly, with 2 also again there are 3 elements of B. So 2, 3, 2, 4, 2, 5. Last we are taking 3, 3, 3, 3, 4, 3, 5. So how many total ordered pairs are there in A cross B? 3, 3s are 9. So that means the number of elements in A cross B, you know already it is number of elements in A multiplied by number of elements in B. This is A cross B. But when you are defining a relation, there can be a number of relations between the elements of set A to B. For example, suppose you are defining a relation, right, that X belongs to A, Y belongs to B, and we say that X is related to Y if and only if X is smaller than Y. Then in this case, while you are calculating and finding the relation, you will consider only those ordered pairs where X is smaller than Y. So you see, out of all this, 1 is smaller than 3, 1 is smaller than 4, 1 is smaller than 5, 2 is smaller than 3, 4, 5, 3 is smaller than 4, 5, but 3 is not smaller than 3. Only this one element will be removed. Rest all 8 entries will be there in relation, right? So 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 3 is removed, 3, 4, and 3, 5. This is a relation. If you say X is the square of Y, in this case, how many odd elements will be there in this relation? Where you see that X is the square of Y. This X and this is Y. So that X is the square of Y. Is there anywhere? No, it is X, but X is not a square of Y is the square of X. So in this case, it will be empty set because in none of the ordered pair, X is the square of Y. A number of relations you can define between the elements of set A to set B. This is how we define the relation. Now we say, suppose we are talking about, say, family of lines. So in a family of lines, L is a capital L representing family of lines. There will be many relations between the lines, like one line is parallel to another, one line is perpendicular to another, one line coincides with another. So these are all the relations, right? In triangles, if I say delta is family of triangles, then one triangle is similar to another, one triangle is congruent to another triangles, right? So this is are all possible relations in the family of geometrical shapes, right? Now suppose there is a set A, as you say now. Suppose set A has two entries, 1, 2, 3. Set B has entries 1, 4, 5, and 9. Now defining here, set A, set B. And you are defining a relation from A to B, that X is related to Y if and only if X minus Y is divisible by 2. Or you can say that X minus Y is the integral multiple of 2. That means the difference is the integral multiple of 2. 1 minus 1, 0 is divisible. 1 minus 5, 4 divisible by 2. 1 minus 9, 8 divisible by 2. Right, 2 minus 1 is not divisible by 2, right? But 2 minus 4 divisible by 2. 2 minus 5 will be 3, which is not divisible by 2. Minus 9, 7 is also not divisible by 2. 3 minus 1, 2 is divisible by 2. 3 minus 4, 1 is not divisible by 2. 3 minus 5, again 2 divisible by 2. And 3 minus 9, 6 is also divisible by 2. So that means in this case, how many ordered pairs are there in the relation you are finding? 1, 1, 1, 5, and 1, 9. Then starting with 2, if you will try here, then 2, 4, can 2 is not there in this case. So 2, 4, only 2, 5, 2, 9, 2, 9 is 7, 2, 5 is 3, 2, 1 is 1, not possible, right? Now with 3, when you come here, 3, 1, 3, 5 and 3, 9. This many ordered pairs are there in this relation. So now comes domain of the relation and range of the relation. Domain and range. Codomain. What is the domain of relation? All elements of set A which are related with the elements of set B, they form the domain. For example, here 1, 2, 3 all are related to some or other elements of set B. So that means when you are finding the domain, all the entries which are related of A to B will come in domain. So here domain will be 1, 2, 3. Right. Now, for example, suppose if I remove 4 from here, then 2 is not connected with any of these relations, so 2 will not come in the domain. In that case, domain will only include 1 and 3. So only domain means domain of relation is the collection of those entries of set A which are related with the entries of set B. It means X belongs to set A, at the same time this ordered pair must be in relation, then only say that X belongs to domain. Codomain means entire set B, all the elements of set B, whether they are connected or not connected, without any restriction, entire set B is called codomain. Range means only those elements of set B which are related with the elements of set A, they will form codomain. So here in this case, codomain as all the entries are connected, 1, 4, 5, 9, this is entire set B. So in this case, codomain is same as range, but it is not necessary. Range is always subset of the codomain. That is important. Okay, always remember. Range of relation is always subset of its codomain. Clear? So range of any relation is the collection of only elements of set A where X is related to Y through relation R. At the same time, whenever X is related to Y through relation R, X belongs to domain and Y belongs to range. So Y forms range, X forms domain. But entire set B is called codomain, right? So this is how we find domain, codomain and range. Sometimes in the question they can ask you additionally that prove and find the domain, range and codomain also. So the concept should be all clear to us. Now the next is types of relations, right? So in your course there are all 3 types of the relations are there. First is reflexive, second symmetric, and third is transitive. So there are 3 types of the relations: reflexive, symmetric and transitive. When a relation is said to be reflexive, for a relation to be reflexive, it is necessary that each and every entry of the relation must be related with themselves. That means A must be related to A and it should be true for all A which belongs to set A. Then the relation is reflexive. For example, if you define a relation of equality, A is equal to B in the set of numbers, then it is reflexive. Why? Because each number is equal to itself. 1 is equal to 1, 2 is equal to 2, 3 is equal to 3, like that. So every number is equal to itself. That means the relation is reflexive. So it should be true for all the entries of set A. That A is related to A, then only the relation is said to be reflexive. For example, if you talk about the family of lines, and I define a relation that a line L is parallel to M. What is about this relation? We know that each line is parallel to itself. because when unless the two lines are parallel, they will not coincide, right? So that means each line is parallel to itself. It's true. Similarly, in family of triangles, every triangle is congruent to itself because it's a replica of the same triangle. So the relation of is equal is parallel to, and the family of lines is a reflexive relation. Similarly, in the family of triangles, a relation is congruent to is also a reflexive relation. So this is how we obtain and find out the reflexive relation. The next is here symmetric relation. When a relation is said to be symmetric. For the relation to be symmetric, it is necessary that A, suppose there is a pair where A is related to B. So if A is related to B, implies that B is related to A. For all such A and B, which belongs to set A. We say the relation R is symmetric. That means wherever A is related to B, B must be related to A. For example, if I say X is a brother of Y, so will this relation be a symmetric relation? Means if I say X is a brother of Y, will Y be also a brother of X? It is not necessary. You know? It depends upon the gender. If Y is a male, then definitely Y will be a brother of X. Otherwise, if Y is female, then Y will be sister of X. It depends upon. So it is not symmetry. So this is mandatory here that whenever A is related to B, there must be B related to A, and should not be true for some, should be true for all sets. That means if I say that a relation is there, for example, no, and say A is having here say 3 elements, no, 1, 2, 3, and relation is defining here 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1. 3, 2, 3, 3. Is this relation symmetric? So suppose if 1, 2 is there, 2, 1 should be there. Is there? Okay. 1, 3 is there, 3, 1 should be there. Then 2, 3 is there, 3, 2 is there. Obviously, the relation is symmetric. If you find one entry or one ordered pair where 1, 2 is there, but 2, 1 is not there in this, then the relation will not be symmetric. So it is necessary that for all such A and B, whenever A is related to B, there must be B related to A. So if we define a relation say in family of lines, that a line is parallel to another line. So we know that two lines are always parallel to each other. So if I say line L is parallel to M, then obviously M is also parallel to L. So that means the relation is parallel to, in the family of lines, is a symmetric relation. Similarly, in family of triangles, if you define a relation is congruent to, so if I say triangle ABC is congruent to PQR, obviously PQR is also congruent to ABC. So that means that relation is congruent to is also a symmetric relation. Now the next comes transitive. For a transitive relation, we talk about three different elements A, B and C which belongs to set A, so that A is related to B and B is related to C. If this together implies that A is related to C, and if it's true for all such A, B, C which belongs to set A, then we say that relation R is transitive. So for a relation to be transitive, we need to check there must be three different entries, so that A is related to B and B is related to C. Together both we can derive this result that A is also related to C with the same relation, so that relation is transitive. That means in this case what we do, we eliminate B and we establish the relation between A and C. For example, if I say in this family of lines this relation is smaller than, so A is smaller than B and B is smaller than C, definitely together it implies that A is smaller than C. So that means the relation is smaller to is a transitive relation. If I think the relation in the family of lines is parallel to, L is parallel to M and line M is parallel to N, together what we conclude, that L is also parallel to n. It's true for all such three lines L, M, N. So that means the relation is parallel to, it's transitive. If we define and think about relation is perpendicular to, will it also be transitive? That means if I say that line L is perpendicular to M and M is perpendicular to N, does it imply that L is perpendicular to N? Let us in the diagram. L is perpendicular to M and M is perpendicular to N. So what is the relation between L and N? They are parallel. So that means this relation is not a transitive relation. So I hope the concept of reflexive, symmetric and transitive relation is clear. What is the reflexive relation? If every entry of a family is related to itself, then we say relation is reflexive. For a relation to check symmetric, there should be two entries that first is related to second. If it implies that second is also related to first, and if it's true for all such ordered pairs, right, then means the relation is symmetric. For transitive, there are three different entries, so that A is related to B and B is related to C. If together it implies that A is also related to C, then we say that the relation is transitive. Right, this is are all varieties and examples, right? And if a relation satisfies all these three conditions, reflexive, symmetric and transitive, then it's called an equivalence relation. Equivalence relation, a relation which is reflexive, symmetric and transitive. All three is called an equivalence relation. For example, in the family of lines, if we define a relation is parallel to, then it's an equivalence relation. How will you write? Reflexive, because you know that each line is parallel to itself. It's a reflexive. And the symmetric, we all know that two lines are always parallel to each other, so it's a symmetric. Transitive, if two lines are parallel to the third line, then both the two lines are also parallel to each other. So that means the relation is reflexive, symmetric, transitive. Finally, right, since the relation is reflexive, symmetric and transitive, all three, hence it's an equivalence relation. Clear? Now we take some more examples from your book of NCERT and to illustrate this difference. In the exercise, there are varieties of questions. Exercise first 1.1, if you take here, determine whether each of the following relations are reflexive, symmetric and transitive. You have to check whether or not, yes or not. If it is, then prove. If it is not, then justify. Justify means through one example you can justify it simply. They are telling in the set there is a relation R defined on set of natural numbers. The relation R is defined as the collection of all ordered pair x, y, where y is 5 more than x and x is smaller than 4. This you can find in terms of ordered pair also. X is a natural number smaller than 4 and y is 5 more than x. That means natural number starts from 1. So if you take x1, what will be y? Y will be 6. If you take x2, what will be y? Plus 5, 7. When you take x3, what will be 5? 8. And when you take 5 less than 3, so only 1, 2, 3. 3 numbers are only possible. So only these 3 ordered pairs are there. Is this relation reflexive? No. Why? Simply one example to write. Since 1, 1 does not belongs to R, it is not reflexive. Symmetric? It's not, because 1, 6 is there, but 6, 1 is not there in the relation. Transitive, there is no continuity, there is no such relation exists. So that means only since the relation is not symmetric, neither reflexive. If it is not reflexive, it cannot be an equivalence relation. But they are asking here to check whether it is reflexive or symmetric or transitive. So every relation you have to check here. So there is no transitivity because there is no continuity, right? So that means the relation is neither reflexive nor symmetric nor transitive. Another example, on the set of integers, the defining a relation as x comma y, where x minus y is an integer, and you know there are integers means three types of the integers: positive, negative and 0. So where x and y are two integers, let's see first one, reflexive. Check the reflexivity of this. Does each integer related to itself? Yes, because if I say 1 is related to 1, why? Because 1 minus 1 is 0, 0 is an integer. So whenever x and y are equal, difference will be 0 and 0 is an integer, which is neither positive nor negative. So to write here the relation is reflexive since x minus x, that means 0, is an integer, which implies that x is related to x for all x which belongs to z. So the relation is reflexive. This implies that R is a reflexive relation. Next, symmetry. Check whether this relation is symmetric. That means whenever, let us say x and y, suppose x comma y belongs to R. So in that case, x minus y is an integer. Now from x minus y to check whether y minus x is also an integer or not. So we know that y minus x is written as minus x minus y. So if x minus y is an integer, it's a negative is also an integer. So it's a negative means y minus x is also an integer. So that means y comma x also belongs to R. That means it is not true for some, it is true for all such x and y which belongs to z. We are assuming let x comma y belongs to R, that means the difference of two integers is an integer. If it is so, let us prove whether the if you change the position or order, will that resulting will also be an integer? Yes, because x minus y, to obtain y minus x we take minus out, and if it is an integer, it's a negative, it's also an integer. So that is the reason. And so whenever x comma y belongs to R, y comma x also belongs to R, that means R is symmetric also. Now let's say for R is transitive, third one. Transitive means you will take here three integers x, y, z, which belongs to z, so that x is related to y and y is related to z. That means what you are assuming here, that x minus y and y minus z both are integers. Okay, they are integers. Can we convert that x minus z is also an integer? So our aim is to eliminate y. So we know that if these two are integers, sum of two integers is always an integer. 2 plus 4 is 6. 2 plus minus 4 is minus 2 is also an integer. So sum of two integers is always an integer. So that logic will give, and so we add both. X minus y plus y minus z is also an integer. So that means finally what we are getting here, that x minus z is also an integer. So that means it's true for all such x, y, z which belongs to capital Z. So that means relation R is transitive. So what we have seen here, the relation is reflexive, symmetric as well as transitive, hence it's an equivalence relation. This is how we check and prove that relation is an equivalence or not. Now I will illustrate one more example. This is also another question given in the NCERT exercise. There is a state given here, 1, 2, 3, 4, 5. And the relation R is defined as collection of all ordered pair A comma B, where A belongs to A, B also belongs to A, and mod A minus B is an even number. We have to show here that this relation is an equivalence relation. First part, right? First part is to prove that this relation is an equivalence relation. The second part is to prove that each entry of the set 1, 3, 5 are related to itself, as well as each entry of the set 2, 4 also related to itself through this relation. But non-entry of 1, 3, 5 is related to 2, 4. Right? So first part we have to prove that this relation is an equivalence relation, and whenever it is asked show that this relation is an equivalence, means it's an equivalence relation, only to write how to do it. So simply first you write that reflexive. So to prove it's reflexive, what you have to prove? Mod A minus A is an even number. You have to prove that each entry A is related to itself A. So prove that mod A minus A, what is A minus A? 0. We know that 0 is always an even number. So write starting from, here we write, since 0 is an even number, that means it implies that mod A minus A is also an even number for all A belongs to set A. This means relation R is reflexive. First part done. Second, to prove that relation R is symmetric, what do you do? You have to assume that there is an ordered pair A comma B which belongs to R. That means mod A minus B is an even number. From mod A minus B, how to bring B minus C? Take this minus out. So it will be minus B minus C is also an even number. And mod of minus is same as mod of plus. This means mod B minus A is an even number. So whenever mod A minus B is an even number, always mod B minus A is also an even number. That means B is also related to A. B comma A also belongs to R, and it's true for all such A and B which belongs to set A. So relation R is symmetric. Now third part is a little bit different than what we discussed. Third part means to prove how relation R is transitive. To prove R transitive, what you will do is assume here that there are three integers or three members of set A, A, B, C. Let A, B, C belongs to set A such that A is related to B, that means A comma B belongs to R, and as well as B comma C also belongs to R. From this, can we convert whether A comma C belongs to R? That means we eliminate B. So that is comes here. It means mod A minus B and mod B minus C both are even number. Now how to eliminate B? You can't write modulus. Mod A plus mod B is not equal to mod A plus B. You know the inequality is mod A plus B is always less than or equal to mod A plus mod B. Right, now it means mod by A minus B is the integral multiple of 2 and mod B minus is also integral multiple of 2. So what we do now, we remove mod, and whenever you remove mod here, it will be plus minus 2m, and B minus C will be equal to plus minus 2n. In any case, whether both are positive, both are negative, one positive, another negative, first negative, second positive, if you have this both equations 1 and 2, B will be eliminated, and you will see A minus C also as a resulting multiple of 2, right? M minus plus n. So ultimately sum of two integers is always an integer. So that means you are getting here A minus C also an integral multiple of 2 here finally. And what we conclude here, that mod A minus C is an even number. So that means relation R is transitive. This is important steps here. Mod A minus B is an even number. Mod B minus C also even. You will remove mod, it will be automatically plus minus on both the side, other side. And when you add both these equations, b will be eliminated, and you see that a minus c is also an integral multiple of 2. So that means it's also an even number. That means R is transitive because it's true for all such ABC belongs to A. So this way we have seen that this relation R is reflexive, symmetric, and transitive. You have write all these three, and hence therefore R is an equivalence relation. This is the first part of the question done. Now in the second part of the same question, we have to prove that each entry of 135 is related to each other. And you know 135 they are all odd numbers, and the difference of two odd numbers is always an even number. That's all simple logic it will be. Each entry of set 1, 3, 5 are related to themselves. Why? Because we know that difference of two odd numbers is always an even number. So that means mod A minus B will always be an even number in case of 1, 3 and 5. This proves that each entry of set A, 1, 3, 5 are related to each other. Second part, each entry of the set which is including 2 and 4 are related to themselves through the same relation. Yes, 2 and 4 both are even numbers, and you know the difference of two even numbers is always an even number. So that means each entry of the set 2 and 4 are related to themselves, and so that is also. But none entry of 1, 3 is related to 4 obviously, because you know the difference of an even and an odd is always an odd number. That means it will never be even. So that means non-entry of 1 to 5 is related to 2, 4. This is the second part. So this way this is question what is asked is done. Now I will discuss one more important concept in this here, that is called equivalence class. If I say equivalence class A, that means you are finding here all those elements of set A which are related with A through well-defined relation. All the elements of set A which are related with this entry A will form its an equivalence class. So equivalence class, I have asked in this question at the end, find equivalence class 1. So which are all elements related to 1 through this relation? 1, 1, 1, 2 or not there? No, 1, 3, 1, 5. These are the elements related to 1. So what will be the equivalence class finally? 1, 3, 5 only. So this was only for explaining you, but the answer is only this set. So this is equivalence class 1. Equivalence class 1 is a collection of all those entries of family which are related with 1, 1, 3, 5. If you write equivalent class 2 here, so all the elements which are related with 2 here, so that is 2, 4, that's all. Only 2 and 4 are related with 2. 2 because difference of 2 even is also an even number. So 2 is related to 2, 2 is related to 4. That's all. So I hope you understand the meaning of equivalence class also. So these were all the concepts. So now you have to practice. We practice all the examples solved and unsolved of the NCERT textbook, as well as for higher order questions you can consult the exemplar of NCERT. In my next class, we will discuss about functions. So have a nice day and practice the questions.